from JNCSR Bangalore in 2008 and postdoc research from Purdue University. Currently, he is an associate professor at ISER Pune. His research areas includes nanophotonics and soft matter physics. He is a member of professional bodies like Optical Society of India, Optical Society of America. He received several awards and honors, including Swarna Jayanti Fellowship in Physical Science 2018 and INSA Medal for Young Scientists 2013. With this brief introduction, I invite Dr. Pavan Kumar for his presentation. Dr. Pavan, please.
Pavan, you are muted. You're muted, Pavan. Pavan, you are muted.
Can you hear me now?
We can hear you.
Yeah. I have shared my screen. I hope it is visible. No.
Screen is visible, but put it full screen.
Full screen. Yeah. I'm trying to do that.
At the bottom.
Yeah. I hope everybody can see this now, right? In the full screen mode.
Absolutely.
Okay. So first of all, a very big thank you to Farook College. I have heard so much about Farook College, and I was extremely glad to get this invitation. First of all, thank you very much. And also very nice to see a lot of people whom I know. Of course, Reggie, who I worked with in JNCSR just beside the lab. It brings back nice memories. And thanks to also Professor Pradeep for this wonderful kind of continuing support and organization of this very important event, which I think is very critical for the science across India. This conference also has a theme of kind of emerging aspects in chemistry, and you'll see that there is a lot of interesting physical chemistry which can also be probed from nanostructures and also right down to the single molecule scale. So in this talk, I'm going to give you some kind of an overview of some of the attempts what we have been making in our lab for the last about 10 years or so at ISER Pune. The interesting aspect also is to ask the role of plasmons in not only just enhancing light matter interaction, but also plasmons have turned out to be probably more vital in providing optothermal fields, which has turned out to be extremely important in various different applications. So I'm going to give you an overview of how one can probe single molecules using gap plasmons. But the talk is mainly kind of pitched at a level where maybe students can also probably appreciate a little bit of the concepts behind it. One caveat I also have to mention is that unlike fluorescence microscopy, here I'll not be talking about an isolated molecule. Okay, this is a very important distinction. What we are talking about is a spectroscopic signature from a single molecule. And that spectroscopic signature would be statistical in nature. So let's see what we can kind of discuss about this concept. Now, confined electromagnetic fields has turned out to be very important. Like as you know, a lot of people have been working on this. In fact, I see that here right away there are at least more than 2-3 people like Professor Pradeep, Pramod. Everybody has contributed to this very interesting field of confined electromagnetic fields facilitated by plasmons. Now, what I'm showing you here is a numerical simulation of what happens if you take 2 gold nanoparticles, which is roughly about 100 nanometers in diameter, and you bring them so close that their distance is much smaller than the wavelength of light, which is incident. Okay, and that particular wavelength of light is roughly around 600 nanometers in this case. Now, if you incident light along the length of this particular dimer of plasmonic nanoparticles, you see that the intensity of the light which you can confine at this dimer region is enormously enhanced. Okay, this enhancement is so high that it can facilitate electric fields up to the scale of 10 to the 7 volt per meter. Okay, so 10 to the 7 volt per meter, if you can compare it to other physical processes, is an enormously large electric field. So much so that you can now look at very interesting chemistry happening at such kind of a confined space. Now, in order to utilize such kind of hotspots, so-called electromagnetic hotspots, you need to also probe molecules in this confined space. So what is of interest in the community is to ask what happens to, let's say, a single molecule, which is now going through this hotspot, or if this particular single molecule is arrested in a hotspot, or what happens to the structure and dynamics of the molecule in this particular hotspot. These are very interesting and evolving questions. There is no final say on what really is happening because, for example, if you put a fluorescent molecule here, they may first of all quench their fluorescence. But if they are placed in a very specific way in this hotspot, you might end up getting some very interesting enhancement of the radiative decays from the molecule. If you have, let's say, a molecule which has a very interesting Raman scattering signal, this molecule can be freely floating in this gap, which means that it is only now subject to an electromagnetic field. Otherwise, the molecule can also now adsorb onto this particular nanoparticle, which means that the surface selection rules govern the modes of vibrations of that particular molecule, and it can give rise to some wonderful and very interesting effects. Now, associated with this kind of processes, generally speaking, is the concept of the power of the interaction in terms of, let's say, the amount of power it is necessary to understand this interaction is given by the product of the cross section, where the cross section is related to either the scattering or the absorption process, times the irradiance, where irradiance is the amount of light you actually are incidenting on such a kind of structure. Now, the power associated with this optical processes can now be divided into two. One is a scattering and the other one is the absorption process. And associated with this is also a cross section, which is a scattering cross section and absorption cross section. Now, the interesting aspect is that this cross section, what we are talking about, is essentially now very much a property of the material what you are taking into consideration. And it happens so that at optical frequencies, the cross section of the scattering and also the absorption of, let's say, gold nanoparticle, or it can be any other kind of noble metal nanoparticles, is supposed to be very high for optical frequency. This is one of the reasons why we extensively use gold nanoparticles and also silver and other kind of particles, because it provides this kind of enhanced interactions, because the solid state aspect of electron density comes into picture, which further facilitates something called as plasmon frequency and also the surface plasmon polaritons, which is a kind of a collective oscillation of light and the electron charge densities in the metal. Now, an important question to ask is, what happens to light emission and heat dissipation from molecules or nanostructures which are now confined to such kind of gaps? Now, these gaps which you are now visualizing are also in essence called as gap-plasmons, because you are creating a very localized optical field because of the plasmons in the gap between two nanostructures. Now, this gap need not be only between a sphere and a sphere. This gap can also be between a sphere and, let's say, a plate, or let's say a two-dimensional surface. So there is now a gap between particle and a film, and that too facilitates very similar kind of electromagnetic fields, but with some very different behavior of the dynamics of plasmons in such kind of electromagnetic fields. So as we progress, we will see what kind of dynamics you will expect in such kind of situations. Now, one of the consequences of creating such gaps is that if you have now a molecule which gives rise to enormous optical fields, and if the molecule happens to be a very good Raman resonator, in the sense if it has a Raman cross section which actually is relatively weak. For example, if you take a thiophenol molecule and you adsorb those kind of molecules onto the nanoparticles which are shown in this transmission electron microscope, what you end up getting is, in the conventional normal Raman scattering, you get a kind of a Raman modes, which are associated with the modes of vibrations of the thiophenol molecule. The moment you adsorb these molecules onto metallic nanostructures, you get enormously enhanced Raman scattering signatures. There are two important features in this spectral signature. One is, of course, that there is an enhancement in the intensity. The other one is that the modes of vibrations, what you're actually observing, need not be the same as what you are observing for a normal Raman scatter signal. This is one of the very important aspects which may be of very high utility in chemistry, where you would be able to understand the local geometry of the molecule and its adsorption dynamics and characteristics by studying the modes of vibrations on a nanoparticle. This has, of course, turned out to be a very powerful tool in catalysis and other kind of interaction, where the geometry of the molecule plays a critical role in the conversion efficiency of a catalytic process. And in order to understand that conversion efficiency, one needs to know the geometry of the molecule on the metallic surface, given that the molecules themselves have very specific kind of bond order and bond kind of the coupling. This plays a very critical role in unveiling some very interesting interactions. So associated with this process is the so-called Raman cross-section. The Raman cross-section in its full glory in quantum mechanics can be understood as a second-order perturbation theory. I would not go into the details of the Raman cross-section, except to mention that the Stokes frequency scales as the fourth power, which means that it goes as inverse to the wavelength to the fourth power. And it is also connected to something called as a resonant Raman process, where if you have now an eigenstate which matches with the excitation laser, omega L is the frequency of the laser, and omega ij happens to be now the eigenstate in that particular molecule. If they matched with each other, then you end up getting a very large resonance. And this resonance can be further utilized for various interesting kind of optical processes. So for your convenience and also for very kind of clear way of looking at the cross section, what is plotted in this particular curve, in this particular graph, is the negative log of cross section, which means the smaller this block, larger is the cross section. So you can see the Raman scattering process, which scales as 10 to the minus 26 or minus 29 in certain cases where there is no resonance characteristics, is a relatively weak process, which means that the Raman cross section actually is very, very weak. Next comes the Rayleigh, then comes the resonant Raman, then the infrared and absorption process, fluorescence, and UV vis. Absorption also plays a critical role. Now, what is of very high interest for this particular talk is that the scattering cross sections related to surface enhanced resonant Raman scattering and surface enhanced resonant Raman scattering can be much more than even the conventional optical processes. Now, this is the reason why SERS and other kind of optical processes have gained so much of attention, because you are now able to determine and detect molecules beyond their conventional cross sections of detection limit, which creates a very new opportunity, and also it creates some interesting problems in this particular field. Associated with this is also the Raman scattering enhancement factor distribution as a function of wavelength. So for example, if you take an ideal geometry of a coupled nanoparticles and you ask how does this enhancement factor vary at the hot spot as a function of the wavelength, you can clearly see that it is not uniform across the wavelength. So what it tells you is that there is now a specific wavelength at which you can operate, which can give rise to a maximum enhancement factor. Interestingly, it is something which is of a very intriguing aspect of this interaction, is that you not only have this wavelength dependence, but you also have the field dependence, which follows some very peculiar statistics. Again, without going into the details, what I would want to mention is that an associated probability density, don't worry about what this specific aspect is. All you need to know is that the enhancement factor, if it scales as a function of the geometry, you see that that particular enhancement factor is maximum for a given particular value of L. In L, in this particular case, is the log of F. If you go back and look at the this particular geometry, what we are talking is about the enhancement factor. Now, the conclusion from this particular analysis is the following. It tells you that this particular enhancement factor follows something called as a Pareto distribution, where you probably would be aware of this very interesting distribution in the context of economics, where, for example, 20% of the population owns 80% of the wealth in a particular country. Now, in surface enhanced Raman scattering, the same Pareto distribution comes into picture, where a 98% of search signal essentially originates from only 2% of the randomly adsorbed molecule in the hotspot. Now, what it tells you is that no matter how many molecules you have in your experiment, what really facilitates the enhancement is only those molecules which are present in the hotspot. So only 2% of that particular molecules really are contributing to almost 98% of the search signal. Now, the next question you have to ask is this enhancement factor good enough to detect single molecules? And the answer is yes. And traditionally speaking, there are two approaches to perform single molecule surface enhanced Raman scattering. One is to use a so-called one analyte approach, where you have one particular molecule of interest at extremely small concentration, so that you have one molecule per nanoparticle. This is the traditional fluorescence microscopy approach or fluorescence spectroscopy approach, where you tend to actually reduce the concentration of the molecule to smaller and smaller values, so that you now have in a volume of interest only one molecule, and you study the signal of your interest from that particular volume. There is another technique called as two analyte technique or a bi-analyte technique, where instead of having extremely low concentration, you have two molecules of relatively similar scattering cross section, and you ask these two molecules to compete for a hotspot, which means that given the statistics of the process, and if you have two molecules which are competing for a particular hotspot, what you end up getting is a very interesting category, which I'm going to allude to as we progress. Now, let's look at some history of this single molecule approach. This was one of the first reports of single molecule statistics in surface enhanced Raman scattering. Now, it is very interesting that they first of all observed fluctuation in the Raman scattering signature. The second of all, they also studied the statistical distribution, and they reported Poissonian distribution. But later on, people came up with a consensus that this Poissonian distribution may not be the most accurate way of looking at this optical process, but it requires a slightly more detailed analysis. And therefore, this approach has not been taken into consideration in the recent single molecule search community. Parallel to this kind of report was this very famous science paper, where people actually reported hot particles quenching the fluorescence and showing huge surface enhanced Raman scattering. This is from Shuming's work, where they took this AFM images of individual nanoparticles, and if you perform surface enhanced Raman scattering across, let's say, A and B, the A generally shows very high, large fluorescence spectra, whereas in B you can see that the Raman scattering signature is much more enhanced compared with fluorescence. This is one of the first reports probably where you find that the fluorescence in the Raman scattering cross sections are inverted. Now, this is something which is spectacular for people who have been doing this kind of spectroscopy, because most of the time it is the other way around. Okay, this is one of the first reports where you will find such kind of inverted process. These two reports gave a lot of confidence, telling that single molecule search can indeed be achieved, but it needed further refinement. One of the important refinements was to actually introduce so-called bi-analyte technique. The bi-analyte technique, which is a very interesting kind of approach to study single molecule spectroscopic signatures, utilizes not a strategy where you do not detect every single molecule, but rather you find out single molecule events. Okay, and importantly, you will end up getting also mixed search signals from both molecules, which are more likely to occur in the particular event. And the signal of interest is purely coming out of the region of interaction. Now, there is a lot of very well written papers by Leroux and Echegon, and a very nicely summarized result in this annual review of physical chemistry, which I strongly recommend, especially for students. And of course, also this book, which I think is a classic in search, which is a very important reading for everybody who would want to pursue this particular field. Now, let me explain this binary experiment in slightly more pictorial and a video-based approach. Now, assume that we have two molecules of interest. One molecule is of it's colored blue. The other molecule is colored red. In this case, I'm taking two different bimolecules. The question we ask is, what is the statistics you actually can derive from this interaction? Okay. Now, there are four different probabilities. One is that only blue molecule is there. The other one is the red molecule. The third one is both the molecules are there in the hotspot, and there is no molecule at all. So the probability of getting this is what is of interest. Now you have an interaction. So for example, you now have a blue molecule coming into the hotspot, then it gives rise to di1 event. Okay. This forms the di1 event. And now the second process is that you now have a red molecule, which now gives rise to the di2 event. Okay. Now, the third process is that you have both the red and the blue molecule in the hotspot. This gives rise to the third event, which is the mixed event. Okay, this mixed event will tell you that both molecules are. And there is another probability where there is no molecule at all, which gives rise to the null event. Okay, this is a very kind of a cartoonish approach to try to explain this process. But what is important is in terms of the statistics. Now, for this kind of experiments, you actually can use various different kind of nanoparticles. In this case, for example, in my group, we had used a kind of a hollow core shell nanoparticle, where essentially you start with a silver particle and you now create a gold shell around that particular particle. You can also tune the plasmons and other things. Now, critical aspect is the following. The critical aspect is now I talked to you about four different events. In this particular case, I have now a Nile blue event. I have a rhodamin 6G event, and I have a mixed event and a null event. From this, you can now extract some very interesting statistical analysis from this particular process, and you end up getting these principal eigenvalues for various different spectra. So you can see the number of spectra we have collected in this whole process is about 15,000 spectra. So you keep actually collecting the signal for a very long time, and you ask what is the distribution of the events in this particular process. And from the principal eigenvalues, you can now extract so-called alpha and alpha dash. I'm not going to go into details except to mention that you now have a covariant axis along beta dash and alpha dash. This tells you what is the probability of both events, or one event, or the other event, or null event. From that, you can now draw a histogram. From that particular histogram, what you end up getting is the probability of the events for a particular molecule and how many events are there. For example, plotted here is the Nile blue events, and the Nile blue events gives you, in this particular situation, an extreme statistics distribution. So what it means is that the probability of getting a mixed event is extremely low, whereas the probability of getting a null event is very high, and the probability of getting the single event is very high. This kind of statistics essentially gives you an experimental proof of a spectroscopic signature of a single molecule in a hotspot. Remember, this is not an isolated molecule in the hotspot, but this is a spectroscopic event arising out of a single molecule in the hotspot. Now, what can you do with this? You can now actually look at these kind of assemblies, and you can ask what are the origins of such kind of assemblies. Now, we further wanted to understand these kind of single molecule events in a dynamic assembly process. So one of the strategies what we use is the following. We now take, let's say, a two-dimensional surface, and this two-dimensional surface has a metal film, in this particular case, a gold film. On top of that is a droplet which contains the gold or silver or any kind of nanoparticle of interest. And now we illuminate this surface, a plasmon. We excite the plasmon, and this creates an optothermal field at the location of interest. And the particles actually now get arrested and get trapped in this particular structure. So let me show you a video of this kind of structure. What you end up also getting is these kind of assembly processes. So So if you now excite the plasmon, what you are seeing is the aggregate of nanoparticles forming at their location of interest. This is a bright field microscopy images. You actually can also utilize dark field image for visualizing such kind of processes. So what you're seeing is a swarm of nanoparticles which have assembled as a function of time. Now, this particular swarm of nanoparticles have some very interesting statistics. For example, if you look at the Raman scattering signature arising out of this kind of a swarm, you now ask, how does the molecular signature fluctuate as a function of time? And you can see what is shown here is a small part of the large experiment. In this particular case, what is plotted is a spectral number as a function of Raman shift. Now you see the fluctuation as a function of time, and you will again go back to the analysis which I spoke about, the bioanalytic technique approach, where you can now extract the statistics out of this particular interaction. Now again, what you see is the proof for the single molecule Raman scattering in such kind of assemblies. And remember, all this is happening with an evanescent optical field. Now, most of the experiments you see in surface enhanced Raman scattering is within focused excitation optical field. This is one of the few proofs where you actually can show single molecule surface enhanced Raman scattering with an evanescent optical field. Now, what is the advantage of evanescent optical field? Is the amount of power you are utilizing for the interaction is extremely low. So this is very critical if you are now looking at, let's say, biomolecules and other kind of sensitive structures which may actually get photo damage. Therefore, this may add some future advantage for such kind of interactions. Now, going further, you actually can do something more interesting. You can now play around with this assembly where you can now take this assembly and move it around at a location of your interest. Now, this is very important if you are doing, let's say, a microfluidics experiment where you want to assemble nanoparticles and then move them around as a function of space and time without having to structure the microfluidic assembly itself. So therefore, it creates some very interesting opportunities for assembly and manipulation of such kind of nanoparticle clusters in an optothermal field. Now you can reversibly switch on and off such kind of assembly. That is, of course, an advantage. Associated with this is also very interesting optical electrodynamic kind of characteristics. There is the hotspot, what I was talking about, which I started with, can now also be facilitated between particle and the film. It can also occur between particle and the particle, and there can be also hotspots created because between the particles which are stacked in the z direction. This provides some very interesting opportunities for manipulation of optical fields. You can now extrapolate this not only from one excitation, but to multiple excitations. So you actually can go from one single excitation to many excitations. And such excitations can lead to some interesting opportunities. For example, now shown here is the excitation at two different regions. In this particular region, the assembly is forming, and there's another formation in another region. What is important is now you also see an assembly which is formed between the excitation points. So here shown here is a very interesting observation of nanoparticle chains purely because of an optothermal field. You have this excitation at these 2 points, but what connects these two nanoparticle assemblies is also a very interesting chain of nanoparticles. Okay, and there is no optical excitation here. It is purely due to an optothermal field, and this thermal field can really create a large chain of nanoparticles all at metal fluid interface. Please remember, this is all happening inside a fluid, which means that you switch off the laser, all these particles go back into your fluid. Okay, so now you can play around. You can also see that this effect is mainly driven by thermal fields, essentially an optothermal field. Because if you switch over the directionality of the excitation, the assembly always happens between the excitation fields, which means that the thermal fields which are now there in this are what are creating the assembly between the excitation points. Furthermore, you actually can extrapolate it to multiple beams, which creates some very interesting situation. For example, you now can take a kind of a isosceles triangular geometry, and what you observe is this. Now you start observing assemblies, of course, at the vertex of the geometry of the triangle. But in addition to the vertex of the triangle, you also see nanoparticles assemble right at the orthocenter of the isosceles triangle. So everybody who knows about the isosceles triangle knows that there is a point called as orthocenter, which essentially is exactly at the central point of these three vertices, and you see exactly the formation happening at the orthocenter. Okay, this is all assembled by optothermal fields because there is no optical excitation at this particular region, but a very nice assembly formation at this particular region. And this gives rise to some very interesting concept of kind of active assembly and optothermal assemblies of nanoparticles. We can also do a cluster tracking analysis and look at the fluctuations. And shown here is the fluctuation as a function of time. The orthocenter assembly is very dynamic, meaning there is a lot of fluctuation in that particular region, but there is always some signal always coming out, whereas other ones are all static because there is a field which is already created. Now, going further, people have utilized these kind of techniques also very interestingly. For example, Yobin Zhang, Ismarjan, and various different people. In fact, for example, the ACS Nano work, which is reported, does actually cite some of our past work where they actually have taken it and also formed something called as thermophoretic interactions, plasmothermal interactions, optothermal tweezers, and other things. In fact, in my lab also we do all these things down to the single nanoparticle scale, and we actually can perform similar experiments. But we are also interested in the questions related to the optothermal fields and the thermoplasmonic aspect of this particular interaction. Now, associated with this, the question you can ask is, can we now shrink these interactions to smaller and smaller scale? In the next few minutes, I will actually try to give you a very brief overview of this particular kind of interaction. For the last several years in my research group, we have been looking at plasmonic nanowires and its interaction with single nanoparticles and colloids and other kind of platforms. We have utilized propagating plasmons not only on the films, but also on various different nanowires. For example, silver nanowires is something which we have been studying for a long time, where you excite the plasmon and it creates very localized optical excitations, but also a kind of a quasi one-dimensional delocalization, which gives rise to very interesting hybrid plasmons, where you can now have a localized plasmon from particle and a propagating plasmon from the nanowire. This creates a unique opportunity to study such kind of interactions in such kind of optical and optothermal fields. And these kind of interactions can also give rise to optical antenna effect, where you can direct light either in the fluorescence regime or even in the Raman scattering regime. So one of the techniques we have developed over the years is something called as backfocal plane imaging, or otherwise also called as Fourier plane imaging, where you can ask, if you have, let's say, a nanoparticle and a nanowire junction, in which direction does the light emit? Can we quantify that particular light? And in order to address this question, we have developed this optical technique. It's called as a backfocal plane optical method. So in a very brief overview, what I need to tell you is that if you have a sample, and if it has points x1, x2, and x3, and if it is emanating light in a particular direction, in the momentum space, all the light which is emanated across the sample, if it happens to be in one direction, they all form a point in the k-space. This is just like normal diffraction, what you have probably come across. All we do is, in the optical technique, we take the backfocal plane image of this particular lens and look at the momentum space distribution of the emerging light from the sample. You cannot actually do this experiment directly at the backfocal plane because high numerical aperture lenses have their backfocal plane right inside the lens. So therefore, you have to create something called as conjugate backfocal plane through some kind of optical processing. And that is what we have actually done. In fact, if somebody is interested in developing or looking at this particular technique, we have an encyclopedia article, and this is also freely available on the archive. So I would request you to actually have a look at that particular thing. Now, this we have really built like a Gaudi's building in the sense we have really piled up a lot of different methodologies, including let's say nonlinear optical techniques, where we can look into momentum resolved light scattering in the optical trapping regime down to the single nanoparticle scales. And this is a very versatile method because this creates a unique opportunity to look at, let's say, second harmonic generation, two photon luminescence, nanoparticle assemblies and nanoparticle traps, which you can create in such kind of situation. And we are now also pushing the limits towards, let's say, single particle trapping and optothermal assembly on various different kind of geometries and other kind of structures. Now, one of the consequences of studying such kind of interaction is to look at what happens if you take a film, a gold film, and you have a silver wire, and you sandwich a molecular layer between them. To begin with, this particular molecular layer, we have used a very well-known molecule like Nile blue layer, but you can now also replace that with two-dimensional kind of chalcogenides and let's say MOS2, graphene, and other kind of stuff. What we have actually observed is something called as extended gap plasmon cavity. Instead of having gap plasmons only at a one particular location, we can now extend this gap plasmon along the length of the wire. Now, what is the consequence? The consequence is now you can now study remote excitation configurations where you can incident light at one location, and you can look at the light which is coming at a remote location. Now, this shown here is a kind of a bright field image overlaid with the optical excitation image. So here you have the plasmon excitation from a 633 nanometer laser. You will see that the light is emanating from the distal end of the wire in the geometry. And if you integrate over all momentum vectors, you will see that the Raman scattering signature is quite intense. Now, if you take the same light and distribute it in the momentum space using the backfocal plane technique, what I'm talking, then you get the distribution in the K space, but it is still integrated over all wavelengths. Now we take a small part of this momentum space and then do spectroscopy in that. So what you find is a very interesting thing. It tells you that the Raman scatter signature is now confined to a large wave vector distribution, whereas let's say an electronic process like fluorescence or photoluminescence is mainly confined to the large wave vectors, and this gives some kind of differential scattering processes, which can be utilized for very confined light matter interactions. Now we also have extrapolated this technique to the nanowire nanoparticle junction, where we see so-called guided modes in this kind of interaction, and this leads to some very interesting characterization of optical fields, all thanks to the surface enhanced Raman scattering. And in this particular experiment, what we have shown is that the nanoparticle only carries the molecules, which means that there are no free molecules in the interaction. And by exciting the Raman dipole between these two nanowire junction, you are now exciting the whole of plasmon, and this plasmon can be directional in nature. It also gives rise to guided modes, and this can lead to some very interesting questions in the nanowire nanoparticle interaction studies. Now we also are trying to do this in such a way that we can perform something called as thermoplasmonic trapping and assembly of colloids. This is a technique on which we have developed on a single crystalline gold triangle, where now you excite this single crystalline gold triangle and you start seeing assembly of colloids around the triangle. And this is all happening on a colloidal substrate. In this particular case, is silica particles, which are roughly around 2.5 to 3 micron in diameter. But we are also now going and performing experiments and from nanoparticles, which are roughly around 200 nanometers or something like that. This gives rise to beautiful two-dimensional crystals of colloids, and all facilitated by the optothermal fields what we have generated. So the prospects are many, and what I have essentially talked about to conclude is that light emission and heat dissipation from molecules and nanostructures can facilitate single molecule surface enhanced Raman scattering. Now, I gave a kind of a broad overview of some of the experiments which have been done in the field and also some of our contribution. There is a lot still to learn from this interaction, because most of the interactions what has been studied is all in the context of very well understood molecules or very well characterized molecules. There is still a lot of scope to be utilized this in, let's say, biomolecular interaction. And there's also several interesting questions. For example, if you, instead of, let's say, taking a small nanoparticle, if you, let's say, take some kind of a cluster of gold. For example, what Professor Pradeep and many other people actually have been extensively studying, that can lead to some very interesting absorption characteristics, which can lead to some very interesting kind of scenario where single molecules themselves are interacting with some particle which are also of the scale of the single molecules. Now, can you distinguish them from each other? What is the kind of optical and optothermal fields such interaction gives rise to? These are probably very interesting questions to ask. In my own group, we are now looking at plasmonic trapping down to the single nanoparticle level. We have achieved it, but we are still actually yet to report that, and hopefully soon we'll be able to do that. And we are also looking at thermophoretic effects, which is something which I have really developed a lot of interest in, where I'm trying to understand optothermal fields of molecules and also biomolecules and other things, which creates some interesting situation. So finally, let me conclude my talk by thanking various different people who are probably the most important people in the context of the work. Current researchers, especially students like Vandana and Deepta, have contributed a lot to this kind of interaction studies. The work was initiated mainly by Partha, who was in Clemers, recently has moved to Finland. He is also now in an industry now. And also this work was also done partly by Rohit, who is a Trinity Fellow in Cambridge now. And of course, the funding comes from various different resources, mainly from Department of Science and Technology, India, and also a few international grants and other things. And the most important thing is, I would thank you all for your patience and for listening to me on a Saturday afternoon, almost. Thank you very much. Thanks a lot.
Thank you. Thank you, Pavan. Now the presentation is open for questions and discussions.
Well, very nice as usual. Fantastic talk. Lots of ideas. And
thank you.
Intense devotion to science.
Yes,
at the same
you
time,
know, all inspired by people like you, especially by you. That I have to mention that. In fact, it dates back to our PhD days where I learned a lot from you and Subbu and everybody.
Intense devotion, at the same time being jovial about it, and that's very, very nice of you. I enjoyed it. Let me ask you one or two things. Obviously, one thing that this optothermal coupling,
yes,
and the consequences of that leading to self-organization,
yes,
is fabulous. Now, that the first is a typical chemist question, that how do you assemble and stop it there so that you create new materials, new matter, right?
Absolutely right.
That matter, you can have all the principles of self-assembly, all that surface functionalization, bring these guys together so that they simply couple. And, so this is a possibility several people could think about using such materials. I mean, you can think of self-organization in polymers, self-organized, well-defined architectures using molecular building blocks, cucurbituryl, cyclodextrin, all that kind of thing would come in.
Absolutely right.
Where is it leading to? Are there any indications in that direction?
Yeah. In fact, I'm very glad that you asked this. This is a very kind of burning question in the field, and people are looking at. There are two applications which have already come out. I'll just give you an overview, but I think there is also many more than this. One is this technique called as printing, where they use this optothermal printing, where you functionalize the two-dimensional substrate on which you are now assembling the structure, and you functionalize such a way that once you form the assembly, it forms a very strong bond between the particle and the substrate. So then, if the solvent is now evaporated, you end up getting the nanoparticle of your interest printed on the two-dimensional substrate. So much so that people have been able to even create pads and other kind of electronic circuits using this particular technique. And people also have been able to assemble individual single nanoparticles. For example, some groups in Germany and also in I think in France, where they have been able to utilize this and able to assemble with a very great accuracy single nanoparticle dimers, such that they are able to form very interesting hotspots in such situations. The second part is that once you have this kind of assembly already formed, people have been now trying to drive some photochemical reactions in that particular volume. And currently there are some reports which tells you that there is some very interesting thing which is happening in such assemblies, because first of all, you have created a very intense optical field, and second of all, you can now induce an external field on top of this and create some new opportunities for catalysis, where they do see some hot electron transfer processes which can be increased and controlled depending upon how you are controlling your excitation potentials and optothermal potentials and other things. So this is something which people have already done this, but there is still a lot of scope because there are only initial processes have been set forth. There is also probably scope for people to play around with the particle of assembly. All the stuff which has been done is just conventional gold nanoparticles. It is something like what we do because those particles are easy to prepare. The real intuition of the chemistry is not been really kind of used. I think there is a huge scope, especially for somebody who can really prepare beautiful particles, and also geometry. Geometry plays a very critical role. This is something, most of us just use conventional spherical particles, but the geometry, for example, having some kind of an anisotropic structure can facilitate some very interesting and new kind of optothermal fields. That is something which people have not really explored. I think there is a lot of scope, and one thing which I find very fascinating is that concept of going to molecular scale, where thermophoretic interactions of molecules has been something people have been very interested now, because now you can assemble molecules literally in this potential. And then you ask what happens, let's say, if you have an inorganic structure which is of the same scale, for example, some kind of the cluster and things like that, because that brings a unique platform to do a real bottom-up process of converting, let's say, a molecular scale element into slightly bigger scale element. And in between, if the molecule is now sandwiched between all these interactions, it can give rise to some very fascinating effects. So that needs very interesting talk between various different aspects of chemistry and these kind of optical processes and other things. So this is my viewpoint, but mine is again a limited viewpoint and only a single viewpoint. There are infinite number of things probably. For example, Professor Richard Zare in Stanford has been doing this for a long time, and I think Professor Graham Cooks and other people have also looked into this interactions inside a droplet. And that is a fascinating area where you can now ask what happens if you have an assembly inside a droplet, because then you can have a control parameter within the droplet, and some very fascinating physics and chemistry is yet to be explored in that particular region.
Sent you a paper that has just been submitted.
Oh, okay, that's great. I'll surely, because I know your group also has done this. In fact, one of the things which we study is also some kind of fluidic interaction. And the book, what you have written with Professor Das is a standard reference we always refer to. There's a lot to learn, and there's a lot to explore. Actually.
So for want of time, let me just ask you one more thing and then stop it here.
Yeah.
What optics, and material interaction, light matter, all that theoretically one can model very well.
Yes.
But here comes another beast of thermal oscillations and all that, another time scale, another length scale and things. So, is it possible that one can model this well, predict assemblies?
Absolutely. In fact, this is one of the very important challenges. See, one can still model thermal fields, but in a continuum kind of approximation. But at a molecular scale, it doesn't really hold good, as you alluded to. So what people are trying to do is some kind of a multi-scale modeling where they can start with, let's say, a continuum model, and also now look at the molecular dynamics simulation, which takes care of the intermediate model. And only in recent times, people have been asking or pursuing this time-dependent density functional theory, which also gives rise to interactions down to the electronic level calculations. My knowledge of the last one is very limited, but I can kind of comment on the first level of this simulations, which we extensively do, the continuum mechanics approach. That works well as long as you are looking at even sub-wavelength optical regime. The moment you bring in molecular interactions, things actually become a little difficult. In fact, one person's work I always try to look up for to understand these kind of processes, Professor George Shah's work. I think he is taking a very nice kind of approach, and they have some very interesting intuition towards this. And of course, there is also David Andrews in UK, who is now looking at molecular quantum electrodynamics processes and things like that. So these two people have some very interesting insight into looking at these interactions. But again, my knowledge of that is kind of limited at the electronic scale. But it's a very important question. It's a very important question because, for example, the concept of temperature, statistical mechanics at a single molecule scale, how do you really define? It's such a complex question to ask. For example, you can always treat the molecules around a biomolecule to be a continuum, but if the molecule is a single entity, associating a temperature to this is something which is difficult. So those questions have to be tackled, and there is no clear answer, at least in my mind. Maybe there is something which is there, which has to be still explored and kind of looked into. Yeah.
Thank you. Thank you very much.
Yeah, thank you very much. My pleasure.